Welcome back to the deep dive. Today, we are tackling something that feels very familiar to anyone who has ever tried to, you know, plan a picnic or a commute
Or just get through a Tuesday.
or to get through a Tuesday, exactly. We're talking about decision making.
Yeah.
But not just any decision making. We're talking about how AI handles the messy, unpredictable chaos of the real world.
It is a fascinating shift. If you remember our previous deep dives, we talked a lot about minimax.
Right.
That was the world of chess or checkers. A world where if you make a move, you have to assume your opponent is a super genius who is absolutely out to destroy you.
Right, the paranoid approach. I remember that vividly. You assume the worst possible outcome for every single move you make, and you plan around that. And in chess, that makes sense.
It does.
You don't expect a grandmaster to just, accidentally knock over his queen. But today we're looking at what happens when you step out of that perfect adversarial world and into, well, actual reality.
Exactly, because in reality, the opponent isn't always a master strategist trying to kill you. Sometimes the opponent is just chance.
Just random.
It's a pair of dice. It's a slippery floor. It's a ghost in Pac-Man that's just wandering around aimlessly.
So the topic today is expectimax search, which sounds a bit like a spell, but it's actually a fundamental shift in how AI thinks. We're moving from planning for the worst-case scenario
To planning for the average case.
the average case.
That's the core mission today. To understand how we calculate utility, what an agent actually wants, and how to make rational decisions when the outcome is uncertain. And we're going to look at the mathematical dangers of being an optimist when you should be a pessimist.
And vice versa, I imagine.
And vice versa.
Okay, let's attack this. We started with minimax, which uses min nodes, that's the AI, looking at all the possibilities and say, if I go left, my opponent will do the thing that hurts me the most.
It's a very defensive way to live. But now we are introducing chance nodes. So think about a robot. The source material uses this great example. Imagine a robot trying to move across a room.
Okay.
In a minimax world, the robot assumes that if it tries to move forward, a malicious enemy might block it. But in the real world, the robot might try to move forward and its wheels just slip.
Right. The floor isn't evil. It doesn't have a vendetta against the robot.
No, it's just slippery. It's just physics.
It's just physics.
Precisely. So instead of a min node where we take the minimum or worst value, we use a chance node. And at a chance node, the AI calculates the expected utility.
Which is a weighted average.
It's essentially a weighted average of all the possible outcomes based on their probability.
I want to slow down and put some real numbers on this because the slides have a calculation that I think makes it super clear.
Okay, good.
So let's say you have a decision to make. 3 possible outcomes. Outcome A, you get 8 points, and there's a 50% chance of that. Outcome B, you hit the jackpot, 24 points, but only a 33% chance.
And outcome C, the disaster.
And outcome C, disaster, you lose 12 points with a 16% chance.
Okay, so let's look at that through the two different lenses. If you were using minimax, you'd look at that minus 12 and you would panic.
Right.
You would assume that outcome is going to happen because you assume the universe hates you. You would value that entire decision at negative 12.
Which means you'd probably never take that action. You'd just stay put because there's a small risk of failure.
Exactly. But expectimax does the actual math. It takes 50% of 8 plus 33% of 24 plus 16% of negative 12.
So it crunches those numbers. 1/2 of 8 is 4.
A third of 24 is 8.
And a 1/6 of negative 12 is negative 2. So you add 4 plus 8 minus 2, and the total is 10.
The total is 10.
So the value of that risky situation is a positive 10. The AI sees that, on average, this is a winning move, even with that chance of disaster.
And that is the breakthrough. The AI chooses the action with the highest average outcome, not the one that avoids the worst-case scenario at all costs. It lets the computer take calculated risks.
Which is something Minimax just can't do.
Minimax is too busy hiding under the bed.
This brings us to my favorite part of the research, the Pac-Man experiments. I love that computer scientists use video games to prove these, heavy mathematical concepts.
It is the perfect test bed. The source material details a series of experiments pitting different types of Pac-Man AIs against different types of ghosts. It's really a battle of ideologies.
The paranoid versus the optimist.
That's a good way to put it.
So let's look at the matchup. First, we have Minimax Pac-Man. This is the Pac-Man who assumes the ghosts are perfect killers. They know exactly where he is, and they are coming for him.
Right, and they tested this Minimax Pac-Man against ghosts that were actually just moving randomly, and the result, Minimax Pac-Man won 5 out of 5 games, survived every time.
Okay, so paranoia works. Better safe than sorry.
It works for survival, yes, but look at the score. The average score was 493. That's okay.
Okay, it's fine. Not amazing.
It's not great. The problem is that the Minimax Pac-Man is inefficient. It spends so much time hiding from ghosts that aren't actually chasing it that it misses chances to eat pellets. It's running away from shadows.
It's like driving 10 miles out of your way to avoid a pothole that might not even be there.
Exactly. So then, enter expectimax Pac-Man, the optimist.
The optimist, I like him already.
He assumes the ghosts are moving according to, a probability model, that they might make mistakes or move randomly.
And when this Pac-Man played against the same random ghosts,
it also won 5 out of 5 games. But the average score jumped to 503.
so it survived and it got a higher score.
Because it wasn't afraid, it knew the odds. It would dive in to grab a pellet near a ghost because it calculated, hey, there's a 75% chance this ghost wanders the other way. It took the risk.
And got the reward.
And got the reward.
This sounds like expectimax is just strictly better. Why would we ever use minimax if expectimax gets a higher score and wins just as often?
Well, here is where it gets really interesting. This is the assumptions versus reality trap.
I can guess where this is going.
The slides highlight a scenario they call dangerous optimism.
What happens when our happy-go-lucky expectimax Pac-Man meets a ghost that actually is a killer?
Total carnage. When expectimax Pac-Man played against an adversarial ghost one that was actively hunting it, it got destroyed.
How badly?
It won only 1 out of 5 games. And the average score, -303.
Ouch. -303. That is a massive failure. It went from hero to 0 instantly.
That is the price of being wrong about the world. Expectimax assumes chance. If the world is actually adversarial, Expectimax walks right into a trap because it thinks, oh, the ghost probably won't eat me.
And then chop.
Chop.
So, the lesson here is about matching your model to your reality. If you're playing chess, be paranoid. If you're playing Pac-Man against random ghosts, be an optimist.
Precisely. The slides call it dangerous optimism, assuming chance when the world is adversarial. But there's also dangerous pessimism.
Right, assuming the worst case when it's not likely, which leads to missed opportunities.
Like our Minimax Pac-Man getting a lower score.
It's a balance. But this all relies on those percentages, right? The whole calculation only works if you know the probabilities.
That is the big challenge. Where do the numbers come from?
I mean, in the robot example, maybe you can test the wheels and say, okay, 10% slippage. But in the real world, it feels a lot messier.
In the real world, it requires modeling. The source gives a great example involving traffic. Let's say you want to know the expected time to get to the airport.
Okay.
You can't control the traffic. It's a chance node. You aren't playing against a traffic wizard who wants you to miss your flight.
Right. So you have to assign weights based on data.
Exactly. The example uses a distribution. 25% chance of none, so no traffic, 50% chance of light traffic, and 25% chance of heavy traffic.
And the times associated are 20 minutes for no traffic, 30 for light, and a painful 60 minutes for heavy traffic.
So to find the expected time, you don't just average 20, 30, and 60, you weight them.
Yeah.
You take 0.25 times 20 plus 0.50 times 30 plus 0.25 times 60.
Which works out to 5 plus 15 plus another 15. The expected time is 35 minutes.
Right, 35 minutes.
Which is interesting because 35 minutes isn't one of the actual options. You'll never actually arrive in 35 minutes.
Yeah, it'll be 20, 30, or 60. But 35 is the number you should plan around. It's the mathematical center of gravity for the decision. And this gets exponentially harder when you combine it with a game that has both opponents and chance.
Like backgammon. The source mentions that backgammon is just a nightmare for AI.
Yes. The slides mention expectiminimax.
Expectiminimax. Try saying that 3 times fast.
I'd rather not. But the concept is wild. In backgammon, you have an opponent trying to beat you.
So you need minimax.
But you also have dice rolls in between every move.
So you need chance nodes.
Exactly. And the branching factor here is just insane.
It's huge.
In chess, you just look at moves. In backgammon, you have to look at every possible dice roll and then every possible move from that roll. The slides note that at a depth of just two moves ahead, there are about 1.2 billion possibilities.
1.2 billion. That's wildly different from chess, where you can look 10, 15 moves deep. Here, you're drowning after 2.
Right. You can't just prune the tree, chop off the bad branches, because you never know if a lucky dice roll might save a bad position.
So what does the AI do?
It forces the AI to be much more dependent on just evaluating the current board state rather than trying to predict the distant future.
I want to shift gears to that word you just used, evaluating. or utility. Because up until now, we've been talking about points or minutes. But AI decision-making is often about preferences.
This is a crucial distinction. Probability is about getting the outcome. Utility is about how much we want the outcome.
The slides have a relatable example, ice cream. You have the state of having a single scoop. You have having a double scoop. And you have the tragic state of dropping the ice cream.
And we can assign values to these. Maybe a single scoop is worth 10 utils. That's the unit of happiness. A double scoop is 20. Dropping it is, I don't know, minus 10.
So utility function just captures these preferences. It tells the AI what to aim for.
Correct. But it's not just about assigning numbers randomly. There are rules. The source talks about rationality.
And this leads to my absolute favorite logical trap in this entire deep dive, the money pump.
Ah, yes, the money pump. This is a thought experiment that demonstrates why your preferences must be consistent. If they aren't, you are doomed.
I want to act this out so everyone understands just how insidious this is. So for an agent or a human to be rational, their preferences have to be transitive.
Transitive, right.
That means if you like A better than B, and you like B better than C, you must like A better than C.
Right. A is greater than B implies A is greater than C. That is logical. But what happens if an agent has a loop? What if they prefer A over B, B over C, but they prefer C over A?
That's the loop. A, B, C, A. It seems harmless, just a quirky personality trait. I like apples more than bananas, bananas more than carrots, but carrots more than apples. Who cares?
The market cares. It seems quirky until you introduce trade. The money pump works like this. Suppose you have an apple. I have a carrot. You prefer carrots to apples, right?
According to my weird loop, yes. C is greater than A, so I'm jealous of your carrot.
So you would probably pay a small amount, let's say 1 cent, to trade your apple for my carrot.
Sure. I trade up, I pay a cent, I get the carrot, I'm happy.
Now you have a carrot. But wait, I have a banana, and you prefer bananas to carrots. B is greater than C.
I do. That banana looks way better than this carrot.
So I offer you the banana. You pay me another cent to trade the carrot for the banana.
Okay. Now I have a banana. I've paid 2 cents total. I'm feeling good.
But wait, look at your preferences again. You prefer apples to bananas.
Oh, no.
A is greater than B.
I see where this is going.
So I offer you an apple. You pay me 1 cent to trade your banana for the apple.
And now I'm back where I started. I have the apple. But I have lost 3 cents.
And I can do it again. And again, I can pump money out of you indefinitely because your preferences are irrational.
That is wild. It proves that rationality isn't just a high-minded philosophical ideal. It's a survival mechanism. If you aren't rational, the world will take all your money.
Exactly. The slides state this clearly. Rational preferences imply behavior describable as maximization of expected utility. If you don't follow the math, you lose. The math protects you from the pump.
But utility isn't always about money, is it? The source mentions some darker units of measurement.
Yes. When we apply this to the real world, we need units for things that are hard to quantify, like life and death. The slides mention micromorts.
Micromorts. It sounds like a tiny wizard, but it's actually kind of terrifying.
It stands for a 1 in a million chance of death. It's used to calculate risk. If a safety feature on a car costs $100 and saves 100 micromorts, is it worth it?
The AI has to put a number on that.
The AI or the policymaker has to put a number on that utility. It feels cold to put a dollar sign on survival, but without it, you can't make the decision. If you value life as infinite, you'd never drive the car. You'd never do anything.
And the other one was QALYs.
QALY, quality adjusted life years. This is used in medical decisions. It's not just about keeping a patient alive for a year. It's about the quality of that year. A year in a coma has a different utility value than a year of full health.
So if an AI is helping a doctor, it might look at 2 treatments. Treatment A gives you 5 years, but you're bedridden. Treatment B gives you 2 years, but you're hiking and swimming.
Exactly. And relying on QALYs allows the system to weigh those options rationally, rather than just looking at time as the only variable.
So to bring this all back together, we've covered a lot. We started with Minimax, the paranoid chess player. We moved to expectimax, the calculated risk-taker who plays the averages.
We learned that expectimax is generally superior in a world of chance. It gets the higher score in Pac-Man. It gets you to the airport faster on average.
But we also learned the fatal flaw. If your model is wrong, if you assume randomness when there is actually an enemy, you end up with a negative score.
You get eaten by the ghost because you were too optimistic.
And we learned that to be safe from the money pump, our preferences have to be consistent. We have to know what we want, and those wants can't contradict each other.
It really changes how you look at daily decisions.
Yeah, every time I decide to speed up to beat a yellow light, I'm basically running a quick expectimax calculation in my brain. Probability of a ticket, low. Utility being on time, high. Probability of an accident, very low.
But the utility is very, very negative.
Very negative.
You are acting as an agent maximizing expected utility. Or at least you're trying to. We humans are not always great at estimating the probabilities. We tend to underestimate the chance node of the police car hiding around the corner.
Very true. We are imperfect machines. Before we wrap up, there was one idea at the very end of the source material that I found really provocative. It challenges the idea of what thinking actually is.
Yes, the reflex vacuum example.
Right. We've been talking about all this complex math, but the slides mention that an agent can be entirely rational.
Yeah.
Meaning it acts as if it were maximizing expected utility without ever actually doing the calculation.
Think of a lookup table for tic-tac-toe. You could write a program that just has a giant list. If board looks like X, do Y. It doesn't know why it's doing it.
Right.
It doesn't know the probabilities or the utilities. It's just following a rule. But the result is perfect play.
So it acts rationally without reasoning.
Exactly. And the vacuum cleaner example is even simpler. If it hits a wall, turn left. If it sees dirt, suck it up. That simple reflex might actually maximize the amount of dust collected.
That leaves me with a big question for everyone listening. If a vacuum cleaner bumps into a wall and turns left because of a simple switch, and it cleans the room perfectly, is it any less rational than a supercomputer that calculated 1 billion probabilities to make the same turn?
Does rationality require thought or just the right action?
It's the ultimate fake it till you make it. If the outcome is optimal, does the process matter? Something to chew on the next time you watch a Roomba bump into your couch. It might be a genius in disguise. Thanks for listening to The Deep Dive.
We'll see you next time.